Imagine you've spent your entire life exploring a single, vast, and completely sealed room. You've mapped every corner, you've studied every object, and you know its properties perfectly. But there's one profound and nagging question left. What's outside the walls? The universe is our room, and tonight we're going to quietly press our ear to that final wall and listen for what might be on the other side. Before we can even begin to ask what's outside the universe, we have to first get a very clear and quiet understanding of what we mean by the universe itself. It turns out that is a much more slippery and interesting question than it first appears. The room we live in is not as simple as it looks. Our journey begins with the first and most fundamental limitation we have. This is our observable universe. This is our cosmic bubble, the small patch of reality that we can see and interact with. This bubble is vast, but it is not infinite. Its boundary is defined by a simple, absolute, and very stubborn law of physics, the speed of light. The universe, as we know, began about 13.8 billion years ago in the Big Bang. This means that the absolute farthest we can possibly see in any direction is the distance that light has had time to travel in those 13.8 billion years. This creates a sphere of observation around us, with the Earth at its very center. The edge of this sphere is our cosmic horizon. Anything beyond that horizon is, for now, completely and totally invisible to us. Its light simply has not had enough time in the entire history of the universe to reach our telescopes.
So what do we see when we look out towards the very edge of this cosmic bubble? What is the wall of our observable room? This brings us to the cosmic microwave background, or CMB. This, as we've explored in other quiet stories, is the oldest light in the universe. It is the faint, cool, and almost perfectly uniform afterglow of the Big Bang itself. For the first 380,000 years of its history, the universe was a hot, dense, and completely opaque fog of plasma. It was a brilliant, glowing haze. Light particles, photons, couldn't travel very far before bumping into a free-roaming electron and being scattered in a random direction. The entire universe was like the inside of a star, or a fog so thick you couldn't see your own hand in front of your face. But as the universe expanded, it cooled. And when the temperature dropped to about 3,000 Kelvin, a critical and beautiful event happened. The universe became cool enough for the free electrons to slow down and be captured by the hydrogen and helium nuclei, forming the first stable neutral atoms. This event is called recombination. And in that moment, everything changed. With all the free electrons now safely bound up inside atoms, the photons that had been trapped in the plasma fog were suddenly set free. The fog cleared. The universe, for the first time in its history, became transparent. The cosmic microwave background is the light from that moment. It is a surface of last scattering, a snapshot, a baby picture of the universe as it was when it first became transparent. When our radio telescopes look at the CMB, they are seeing the glowing wall of that ancient plasma fog, which surrounds us in every single direction we look. We cannot see past this wall with any conventional telescope, because the universe before it was opaque. So the cosmic microwave background is the effective boundary, the beautiful, ancient, and glowing wallpaper of our observable universe.
This baby picture of the universe is astonishingly uniform. The temperature of the CMB is almost perfectly the same everywhere we look, at a steady 2.725 degrees above absolute zero. But it's not perfectly uniform. Thanks to incredibly sensitive satellites like the Planck spacecraft, we have mapped out tiny, almost imperceptible fluctuations in that temperature. These are differences of only 1 part in 100,000, but they are the most important features in the entire cosmos. These tiny ripples, these slightly hotter and slightly cooler spots in the ancient light, were the primordial seeds of all the structure we see in the universe today. They were the tiny density variations, likely created by quantum fluctuations in the first moments of the Big Bang, that gravity would later act upon. Over hundreds of millions and billions of years, the slightly denser, slightly cooler spots had a little bit more gravity. They began to pull in more and more material, first dark matter, and then the normal gas. These were the seeds that would eventually grow into the first stars, the first galaxies, and the colossal superclusters that make up the cosmic web. Every single thing we see in the universe today, our own Milky Way galaxy, our sun, our planet, and even you, owes its existence to one of these tiny, quiet, random fluctuations in the baby picture of the universe. It's a profound and humbling thought that all the complexity and beauty of our cosmos is just the amplified echo of a tiny quantum whisper from the very beginning of time. This also leads us to a beautiful and slightly strange thought. Because the light from the CMB has taken 13.8 billion years to reach us, we are seeing it as it was 13.8 billion years ago. And because we see it in every direction, it means we are, by definition, at the very center of our own observable bubble of reality. Our position in the cosmos, from our own point of view, seems to be a very special one indeed.
This brings us to a quiet and important clarification about our place in the cosmos: the illusion of the center. The fact that we appear to be at the center of our own observable universe is not a sign that we are special or that our location is in any way privileged. It is simply a logical consequence of the fact that we are the ones doing the observing. An observer in a galaxy a billion light years away from us would see themselves at the very center of their own observable universe. And from their perspective, our own Milky Way galaxy would appear to be near the edge of their cosmic horizon. It's a bit like being on a ship in the middle of a vast, foggy ocean at night. Your horizon, the edge of what you can see, forms a perfect circle around your ship. You are, by definition, at the center of your own visible world. But a sailor on another ship, a few miles away, is also at the center of their own, slightly different circular horizon. There is no one true center of the ocean. The center is simply wherever the observer happens to be. The same is true for the universe. The Big Bang did not happen at a single point in space, like an explosion in an empty room. It was the expansion of space itself, happening everywhere at once. So there is no physical center to the universe from which everything is expanding away. Every point in the cosmos can be considered the center of its own observable bubble. It's a quiet, democratic, and deeply humbling idea. It removes any last vestige of our ancient pre-Copernican desire to be at the center of everything. We are not special. We are just one point of view among a potential infinity of others. And this brings us to the first, simplest, and most scientifically straightforward answer to our great question: what lies outside our observable universe? The quiet and most likely answer is simply more universe. The cosmic horizon, the edge of our observable bubble, is not a physical wall. It is a horizon of information, a limit imposed by the finite age of the universe and the finite speed of light. There is absolutely no reason to think that the universe just stops at the edge of what we can see. The universe beyond our horizon is, in all likelihood, just more of the same. More quiet, empty voids, more vast web-like filaments of galaxies, more clusters and superclusters, more stars, more planets, and perhaps more quiet minds wondering what lies beyond their own horizons. But how much more? This is where the story gets truly mind-boggling and the scale becomes almost laughable. Our best theory for the very early universe is cosmic inflation. As we know, this is the idea that in the first fraction of a second, the universe underwent a period of hyper-fast exponential expansion. The amount of expansion during inflation was so immense, so ridiculously large, that the entire universe today is likely to be vastly, almost infinitely larger than the small 93 billion light-year wide bubble that we can see. The most conservative estimates from our inflationary models suggest that the entire universe is at least trillions upon trillions of times larger than our observable universe. But it could, in fact, be truly, mathematically infinite. So the first answer to what's outside our universe is a quiet and humbling one. Outside our observable universe is just an unimaginably vast and perhaps infinite expanse of more of our own universe, a cosmic ocean of galaxies that we can never ever see or interact with because it is so far away that its light will never have enough time to reach us.
Let's just quietly sit with the implications of this for a moment, because they are profound, strange, and a little bit dizzying. If the universe beyond our horizon is truly infinite, and if it is filled with a roughly uniform distribution of matter and energy, then a strange and almost magical statistical conclusion seems to follow. An infinite universe must contain an infinite number of every possible thing that is allowed by the laws of physics. This means that somewhere out there in the unobservable depths of our own universe, there is another galaxy that is an exact atom for atom, quantum state for quantum state, perfect replica of our own Milky Way. And somewhere out there, there is another one, and another one. In fact, in an infinite universe, there must be an infinite number of them. And it gets much more personal and much weirder than that. It means that somewhere out there in a distant, unreachable galaxy, there is another star that is a perfect copy of our Sun, and orbiting it is another planet that is a perfect copy of our Earth. And on that planet, there is a person who is an exact atom for atom replica of you, living a life that has been identical to yours up to this very moment. And there are an infinite number of these cosmic twins. And it gets even stranger. In an infinite universe, every possible variation must also exist somewhere. So there is a version of you out there that chose to have a different breakfast this morning. There is a version of you that decided to pursue a different career or live in a different country. There is a version of you that is a wildly successful pirate captain. And there is a version of you that decided to wear a truly questionable hat this morning. Every single possible outcome of every single choice you have ever made is being played out, right now, by another version of you in some distant, unreachable part of an infinite cosmos. It's a quiet, statistical, and deeply strange thought. So this first and simplest answer to our question, that outside is just more of the same forever, is a beautiful and mind-expanding one. But it's an answer that depends on the overall shape or geometry of our universe. This brings us to our next quiet chapter in this story, the shape of everything. According to Einstein's theory of general relativity, space-time is not just a passive stage on which events unfold. It is an active, dynamic fabric that can be bent, curved, and shaped by the matter and energy within it. And the universe as a whole must have a certain overall geometry. There are three basic possibilities for the shape of our universe, and each one has a very different implication for the question of what lies outside. The first possibility is a closed universe. In this scenario, the density of all the matter and energy in the universe is greater than a certain critical density. If this were the case, the combined gravity of everything would be strong enough to overcome the expansion, and it would pull the universe back in on itself. In this model, space-time would be positively curved, like the surface of a giant, four-dimensional sphere. Now, this is where it gets interesting. A closed spherical universe is finite in size, but it is unbounded. Let's think about that with a simple two-dimensional analogy. Imagine you are an ant living on the surface of a giant balloon. You can walk forever in one single direction and you will never ever reach an edge or a boundary. You will just eventually, after a very long journey, end up right back where you started. The surface of the balloon is finite. It has a finite number of square inches, but it has no edge. A closed universe would be the three-dimensional equivalent of this. It would be a finite cosmos, but it would have no outside, because it would curve back in on itself in a higher dimension. So if our universe were closed, the answer to what's outside would be a simple, quiet nothing, because the very concept of outside would be a meaningless question.
The second possibility is an open universe. This would happen if the density of the matter and energy in the universe is less than the critical density. In this case, there is not enough gravity to ever stop the cosmic expansion. The universe would expand forever. And in this scenario, space-time would be negatively curved. The two-dimensional analogy for this shape is the surface of a saddle, or perhaps a Pringle chip, a shape that curves outwards in all directions. An open, saddle-shaped universe is, by its very nature, infinite in extent. It would stretch on forever in every direction. The third and final possibility is a flat universe. This is the special borderline case. This would happen if the density of the universe is exactly equal to the critical density. In this case, there is just enough gravity to slow the expansion down, but not quite enough to ever stop it completely. The expansion would continue forever, but it would get slower and slower, approaching a speed of zero after an infinite amount of time. In this Goldilocks scenario, the universe would have no overall curvature. It would be perfectly, geometrically flat, like an infinite, four-dimensional sheet of paper. A flat universe, like an open one, is also infinite in extent. So, which one of these three possible universes do we live in? Do we live in a finite sphere, an infinite saddle, or an infinite flat sheet? This is one of the most fundamental questions in all of cosmology, and for decades we have been trying to measure the shape of our cosmos. And our best measurements, particularly from the detailed maps of the cosmic microwave background, have given us a clear and very, very strange answer. As far as we can possibly measure, with incredible precision, the universe appears to be perfectly flat.
The fact that our universe is so perfectly flat is a quiet and profound mystery in itself, the flatness problem that we've discussed before. It's a very special and unstable state, like a pencil balanced perfectly on its sharpest point. Even a tiny deviation from perfect flatness in the early universe should have been magnified enormously over 13.8 billion years of expansion. The fact that we find ourselves in such a perfectly balanced universe is one of the key pieces of evidence for the theory of cosmic inflation, which, as we know, provides a beautiful explanation for how the universe could have been stretched to the state of perfect flatness. But for our purposes tonight, this observation has a profound implication. The fact that our universe appears to be flat strongly suggests that it is, in fact, infinite in size. And this brings us back to our first, quiet, and most scientifically supported conclusion. The simplest answer to the question, what is outside our observable universe, is an almost infinitely vast expanse of more of our own universe, stretching on forever, filled with more galaxies, more stars, and more quiet, endless space. But this is not the only possibility. Our science, at its very bleeding edge, hints at other, much stranger, and much more spectacular answers. It hints at the possibility that our entire universe, as vast and as infinite as it may be, is still just one single isolated entity in a much larger and much more bizarre cosmic reality. And this brings us to our next great chapter in our quiet journey. We are now leaving the relatively comfortable and scientifically grounded territory of our own universe, and we are venturing into the realm of pure, speculative, but scientifically motivated theory. We are going to explore the quiet, mind-bending, and beautiful idea of the multiverse.
The fact that our universe is so perfectly flat is a quiet and profound mystery, the flatness problem. But for our purposes tonight, this observation has a profound implication. The fact that our universe appears to be flat strongly suggests that it is in fact infinite in size. And this brings us back to our first quiet and most scientifically supported conclusion. The simplest answer to the question, what is outside our observable universe, is an almost infinitely vast expanse of more of our own universe, stretching on forever. But this is not the only possibility. Our science, at its very edge, hints at other, much stranger answers. It hints at the possibility that our entire universe, as vast and as infinite as it may be, is still just one single entity in a much larger and much more bizarre cosmic reality. And this brings us to our next great chapter.
All right, let's take another slow, deep breath and allow our minds to expand. We are now leaving the relatively comfortable territory of our own universe, and we are venturing into the realm of pure, speculative, but scientifically grounded theory. We are going to explore the quiet, mind-bending, and beautiful idea of the multiverse. The multiverse is not just a single idea. It's a collection of different scientific theories, all of which, for very different reasons, point to the same incredible conclusion. Our universe may not be the only one. These theories are not wild fantasies. They are the plausible and, in some cases, the almost inevitable logical consequences of our best current models of the cosmos, particularly string theory and cosmic inflation. So let's take a quiet, walking tour through the different possible kinds of multiverse, the different ways that reality might be grander than we ever thought. Our first and perhaps most popular version of this idea comes directly from the theory of cosmic inflation we discussed earlier. This is the inflationary multiverse. As we know, inflation is the theory that our universe underwent a period of hyperfast, exponential expansion in its first fraction of a second. The theory that best describes this, a model called eternal inflation, suggests that this process of inflation might not have been a one-time event that happened and then stopped. Instead, it could be the default state of the cosmos. It could be happening continuously on a much grander scale. Imagine a vast, eternally expanding metaverse, an ocean of inflating space-time driven by the energy of a hypothetical inflaton field. Within this ocean, different regions can, at random, stop inflating and settle down into a more stable, lower energy state. Each time this happens, a new bubble universe is born. This bubble would then experience its own hot Big Bang and would expand and evolve on its own, completely isolated from all the others. Our entire, vast, and possibly infinite universe would be just one of these bubbles in an eternally frothing cosmic foam of new universes.
This idea of an inflationary multiverse is a beautiful and powerful one. It paints a picture of a cosmos that is constantly creating, a fractal of new realities budding off for all eternity. But it has a strange and profound implication. Each of these bubble universes could, in theory, have its own unique set of physical laws and fundamental constants. The reason for this lies in the complex world of string theory, which we'll get to shortly. But the basic idea is that the fundamental laws of physics might not be fixed. They might just be the result of how the extra dimensions of space-time curled up and settled down after the Big Bang.
And in each new bubble universe, they could curl up in a different way, leading to a completely different set of physical laws. So outside our universe could be another bubble universe where the force of gravity is 1,000,000 times stronger, or a universe where there are only 2 dimensions of space instead of 3, or a universe with a completely different set of fundamental particles and forces, a reality so alien we couldn't even begin to imagine it. This provides a quiet and elegant solution to the fine-tuning problem we've discussed before, the mystery of why our own universe seems so perfectly calibrated for the existence of life. The anthropic principle in this context becomes a simple matter of statistics. In an infinite multiverse, where every possible combination of physical laws exists somewhere, it is no longer surprising that we find ourselves living in one of the rare bubbles where the laws happen to be the right ones for stars, planets, and people to exist. We have to be in such a universe because we couldn't exist anywhere else to ask the question. It's a quiet and humbling thought that our entire reality might just be one lucky bubble in an infinite cosmic foam.
Now let's turn to another, equally strange and beautiful, path to the multiverse. This one comes from our best attempt so far to create a theory of everything, a single unified theory that can describe all the forces of nature, from gravity to quantum mechanics. This is the strange and wonderful world of string theory. The central idea of string theory is a simple and elegant one. It suggests that the fundamental constituents of reality are not point-like particles, like electrons and quarks. Instead, it proposes that at the very smallest, most fundamental level, everything is made of tiny, one-dimensional, vibrating strings of energy. An electron is just a string vibrating in one particular pattern. A photon is a string vibrating in a different pattern. A quark is yet another. The entire zoo of different particles we see in the universe is just the different notes or harmonies of these fundamental cosmic strings. It's a beautiful idea that unifies all of matter and energy into a single, elegant, musical framework. But for the mathematics of string theory to work, it requires something very strange. It requires that the universe have more than the 3 spatial dimensions we are familiar with. In fact, the most popular version of the theory, M theory, requires the existence of 10 spatial dimensions and 1 time dimension. So where are these other 7 dimensions? The theory suggests that they are curled up or compactified at an incredibly tiny scale, far too small for us to ever see or interact with directly. It's a quiet, mind-bending idea that the rich, 3-dimensional world we experience is just a small part of a much larger 10-dimensional reality. And this idea of hidden dimensions leads to its own unique and very strange version of the multiverse. This model of the cosmos, which comes from string theory, is called brain cosmology. In this view, our entire familiar 3-dimensional universe is what is known as a brain, a membrane that is floating in a higher dimensional space called the bulk. Let's try a quiet, simple analogy. Imagine that our universe is a single, flat, 2-dimensional sheet of paper, floating in the 3-dimensional space of a large, dark room. As 2-dimensional beings living on the surface of that paper, we could only ever perceive length and width. We would have no concept of up or down. The 3rd dimension of the room would be completely inaccessible and invisible to us. Brain cosmology suggests that our reality is like that. We are 3-dimensional beings living on a 3-dimensional brain, which is floating in a higher dimensional, perhaps 10-dimensional, bulk. And what if there are other sheets of paper, other brains, floating parallel to our own in that higher dimensional room? This is the string theory multiverse. It is the idea that outside our universe could be a higher dimensional space containing other parallel universes,
perhaps only a fraction of a millimeter away from us, but completely inaccessible because we and all the forces of our universe, except gravity, are confined to our own three-dimensional brain. It's a quiet, ghostly, and deeply strange idea. The notion that another entire reality could be right next to us, hidden in a direction we can't even point to. It suggests that the answer to what's outside the universe is not a distant place, but a hidden dimension.
This idea of brain cosmology also provides a speculative and very dramatic new theory for the Big Bang itself. In some versions of the theory, the Big Bang was not the ultimate beginning of time. Instead, it was caused by the collision of two of these parallel brain universes in the higher dimensional bulk. Imagine two of those vast, cosmic sheets of paper floating silently in the darkroom, and imagine they slowly drift towards each other until they gently touch. The collision of these two three-dimensional universes would release a colossal amount of energy, creating the hot, dense, rapidly expanding state that we call the Big Bang, and setting a new universe in motion. It's a beautiful idea of a cyclical universe, where the end of one cosmic era, in a fiery but quiet collision, is the beginning of the next. Finally, we come to the third and perhaps most personal and most bizarre version of the multiverse. This one comes not from cosmology or string theory, but from the strange and well-tested rules of the quantum world. This is the quantum multiverse, also known as the many worlds interpretation. As we know from the double-slit experiment, a quantum particle, before it is measured, seems to exist in a fuzzy superposition of all its possible states at once. The standard interpretation of quantum mechanics, the Copenhagen interpretation, says that when we make a measurement, this cloud of possibilities collapses into a single, random, definite reality. But this idea of collapse has always been a bit of a strange and unsatisfying concept for many physicists. It seems to give a special, almost magical role to the act of measurement. So in the 1950s, a physicist named Hugh Everett III proposed a radical, quiet, and deeply strange alternative. He suggested that the wave function never collapses at all. Instead, every single time a quantum event with multiple possible outcomes occurs, the entire universe itself splits into multiple, non-communicating branches.
In this many worlds interpretation, every single possible outcome of every single quantum event is real. It just happens in its own separate, parallel universe. Let's go back to Schrödinger's cat. In the standard view, the cat is both alive and dead until you open the box, at which point reality randomly chooses one outcome. In the many worlds view, when you open the box, the universe itself splits in two. In one branch of the universe, you open the box and find a living cat. And in another, completely separate parallel branch of the universe, an identical version of you opens an identical box and finds a dead cat. Both outcomes are real. This is a quiet, staggering, and almost incomprehensibly large vision of reality. It means that every single quantum event, happening trillions upon trillions of times every single second, all across the universe, is constantly splitting our reality into an endlessly branching, ever-multiplying tree of parallel timelines. This is a much more personal kind of multiverse. It means that there is another universe that is exactly the same as this one, except that you chose to have a different breakfast this morning. There is another universe where you took that different job, or pursued that different relationship. There is a universe that contains every single possible outcome of every single choice you have ever made, and every choice you ever could have made. In this view, outside our universe is an infinite sea of almost identical parallel realities, each one representing a slightly different version of our own history. It's a quiet, humbling, and deeply strange idea. We have no way of testing it, and no way of ever communicating with these other versions of ourselves. But it remains a valid and, for many physicists, a mathematically elegant solution to the strange puzzles of the quantum world.
So we have explored the scientific possibilities for what lies beyond our universe. Outside could be just more of our own universe, stretching on for eternity. Or it could be an infinite foam of other different bubble universes. Or it could be a higher dimensional space with parallel worlds floating nearby. Or it could be an endless, branching tree of parallel quantum timelines. But what if the answer is even stranger than that? What if the very question we are asking is based on a flawed assumption about the nature of reality itself? This brings us to our next great chapter in this quiet journey. We are now leaving the realm of physics and entering the realm of philosophy to explore an idea that is both ancient and thoroughly modern. In this next great hall of our museum, we will explore an idea that has captivated thinkers for centuries, but which has been given a new and powerful form in our modern digital age. This is the simulation hypothesis. The core idea is a simple one. It's the quiet, unsettling suggestion that our entire, vast, and seemingly physical universe might be, in fact, an incredibly advanced computer simulation. The reality we experience might not be the base reality, but a program running on some unimaginable computer in another, higher reality. This idea, in its modern form, was most famously laid out as a serious philosophical argument by the Oxford philosopher Nick Bostrom in 2003, and it is a quiet and surprisingly logical statistical argument. It is not a proof, but a powerful puzzle. Let's walk through his trilemma slowly. A trilemma is a choice between three difficult possibilities, one of which, he argues, is very likely to be true.
The first possibility, or lemma, is that any civilization that reaches a level of technological maturity capable of creating perfectly realistic, simulated universes with conscious beings inside them will almost certainly destroy itself before it gets there. This is another version of the great filter idea. If this is true, then we are almost certainly not living in a simulation because no one ever gets to the point of being able to create one. But it is, as we've said, a rather grim outlook for our own long-term future. The second possibility is that advanced civilizations do reach this post-human stage of technological maturity, but that for some reason, perhaps for deep ethical reasons or a lack of interest, or because it is too computationally expensive, almost none of them ever have any desire to run ancestor simulations like ours. If this is true, then again, we are probably not in a simulation because the number of simulated universes being created would be very small. The third possibility is the crucial one. It is the idea that an advanced civilization would be able to create such simulations and that they would have reasons to run many, many of them. They might run them for scientific research, to study the laws of physics or the evolution of life. They might run them for art or for entertainment. Or they might run them for reasons so advanced and so alien that we couldn't even begin to comprehend them. If this third possibility is true, then a simple, quiet, and powerful statistical conclusion seems to follow. Over time, the number of simulated universes, with their countless simulated conscious beings living inside them, would grow to be colossal. There would be billions upon billions of these simulated realities. And there would be only one single, base reality where the computers running all these simulations exist.
So, if you are a conscious being, like you are right now, and you know nothing else about your own reality, what is more probable? That you are one of the incredibly rare beings living in the one and only base reality? Or that you are one of the trillions upon trillions of simulated beings living in one of the countless simulated realities?
The quiet statistical answer is that the odds are overwhelmingly in favor of you being in a simulation. This is the quiet logical core of the simulation argument. It doesn't prove that we are in a simulation, it just argues that it is a very, very high probability. And this idea completely reframes our question of what is outside the universe. In this scenario, outside our universe is not another physical reality in the same sense. Outside our universe is the base reality. It is the world where the computer that is running our simulation exists. It is the place of the programmers. And this outside world could be completely, unimaginably different from our own. It might not even be a physical world. It could be a purely digital reality itself, with our simulation just being a program running within another larger program. And the laws of physics that we have spent so long studying, that seem so fundamental and so eternal to us, they are not fundamental laws of reality at all. They are just the rules of the program. They are the lines of code, the parameters of the simulation, written by its creators. Gravity is just a subroutine. The speed of light is just a variable in the code. It's a quiet, dizzying, and deeply strange thought. It suggests that the very fabric of our reality might be, in a sense, artificial.
This leads to a fascinating, quiet question. If we are living in a simulation, could we ever find the evidence? Could we find the glitches in the matrix? Some scientists and philosophers have quietly speculated on this. One idea is to look at the very smallest scales of reality. Our universe seems to be continuous, but if it were a computer simulation, it would have to be running on some kind of computational grid. This means that at a very, very small scale, space-time itself might not be smooth, but might be made of discrete, tiny pixels, just like the image on your computer screen. The smallest possible unit of space is thought to be the Planck length, an incredibly tiny distance. Some have suggested that if we could ever build an instrument powerful enough to probe the universe at this scale, we might find evidence of this underlying pixelated structure, the source code of our reality. Another place to look for glitches is in the laws of physics themselves. Are they perfectly consistent? Or are there small, quiet anomalies that might hint at the simulation's code being imperfect or being updated? The slight discrepancies we see in our measurements of certain fundamental constants, or the strange anomalies in the cosmic microwave background we've discussed, have been, by some, playfully suggested as potential evidence of this. But the simulation hypothesis is, at its heart, a deeply philosophical and perhaps unfalsifiable idea. Any evidence we found could simply be a part of the simulation's code, deliberately placed there by the programmers. And any lack of evidence just means the simulation is very, very good. It is a perfect, looping, philosophical puzzle. But it provides a quiet and strangely comforting answer to our great question. Outside the universe is simply the next level up.
Does it even matter if we live in a simulation? If the program is perfect, if the simulation is completely indistinguishable from a base reality, then in what meaningful sense is it not real? It's a quiet, dizzying, and perhaps ultimately unanswerable question. The simulation hypothesis is a perfect piece of philosophical machinery, a thought experiment that forces us to question the very foundations of what we consider to be real. And it provides a strange and elegant, if unprovable, answer to our great question. Now let's turn to another profound philosophical idea that relates to our place in the cosmos. In our quiet journey through the quantum labyrinth, we saw how the act of observation seems to be fundamentally entangled with the reality it is observing. This leads to a strange and speculative branch of thought that takes this idea to its ultimate conclusion. This is the realm of consciousness and reality. We begin with what is often called the hard problem of consciousness. As we've discussed, this is the deep and seemingly unbridgeable gap in our scientific understanding of how the physical processes of the brain, the firing of neurons, the exchange of chemicals, create the rich, subjective, first-person experience of being you. How does a collection of atoms and electricity produce the feeling of warmth from the sun, the beauty of a piece of music, or the very thought you are having right now? Science is very good at describing the objective, external world of matter and energy, but it has, so far, completely failed to explain the subjective, internal world of experience. This has led some philosophers and scientists to wonder if we are looking at the problem backwards. This leads to a very old philosophical idea called idealism. The idea is that consciousness, not matter, is the fundamental stuff of reality. The physical world, in this view, is a manifestation of consciousness, not the other way around. The universe is not a machine that happens to produce consciousness. It is a thought in a great cosmic mind.
This is, of course, a deeply philosophical and metaphysical idea, and it is not a part of mainstream science. But it has a strange and fascinating echo in some of the more speculative corners of theoretical physics. One of these is a concept proposed by the great physicist John Archibald Wheeler, who gave us the delayed choice experiment. He called it the participatory anthropic principle. Wheeler was deeply puzzled by the role of the observer in quantum mechanics. He took the idea to its logical, cosmic conclusion. He pointed out that the light from a distant quasar, which has been traveling for billions of years, can be gravitationally lensed by an intervening galaxy, forcing it to take two different paths to reach us on Earth. When we on Earth set up an experiment to observe that light, our choice of how to observe it, whether to look for its wave-like properties or its particle-like properties, seems to determine which path it took billions of years ago. Wheeler used this to propose a radical idea. He suggested that the universe itself, in its earliest moments, existed as a fuzzy, quantum superposition of all possible histories, and that it was only the emergence of conscious observers, like us, billions of years later, that provided the act of measurement needed to collapse that wave function and make the universe's history real. In this strange, quiet, and deeply unsettling view, we are not just passive observers of the cosmic story. We are active participants in its creation. We are, in a sense, the reason the universe exists in the form that it does. Outside the universe, in this view, was just a sea of unobserved potential, a quiet quantum foam, waiting for a conscious mind to look at it and give it a history. It is a profound and beautiful, if deeply unprovable, idea.
Another quiet and profound idea that touches upon the relationship between reality and the mind is the mathematical universe hypothesis, proposed by the physicist Max Tegmark. This is a potential solution to the paradox of the unreasonable effectiveness of mathematics that we discussed earlier. The hypothesis is a simple, if mind-bending one. It suggests that our universe is not just described by mathematics, it is a mathematical structure. The idea is that there is no distinction between the physical world and the abstract world of mathematics. Every single thing in our universe, from a subatomic particle to a giant galaxy, is a purely mathematical object. A particle's properties, like its mass and its charge,
are not properties of the particle, they are the particle. The particle is just a set of numbers. And the laws of physics that govern how these particles interact are just the mathematical equations that define the relationships between these numbers. In this view, our entire reality is a single, vast, and incredibly complex mathematical object. We are, ourselves, self-aware substructures within this larger mathematical object. We are, in essence, living thoughts in a mathematical dream. What does this say about what is outside the universe? The mathematical universe hypothesis suggests that every possible mathematical structure that can exist does exist as its own separate self-contained universe. So there would be other universes based on different and perhaps much stranger mathematical systems with different dimensions and different laws. Outside our universe, in this view, is a vast, abstract, and timeless Platonic realm containing every single mathematical shape and equation that is logically possible. It is a quiet, elegant, and deeply strange vision of reality, a universe made of pure, beautiful, and unadulterated thought.
Now let's leave these strange philosophical ideas about the nature of reality and turn our attention to one last set of quiet puzzles. A series of ancient and modern paradoxes that explore the nature of identity, logic, and infinity. Let's return to that quiet, beautiful puzzle from ancient Greece, the ship of Theseus. We know the story. A ship is preserved by replacing every single one of its planks over 100 years. The quiet question is it still the same ship? And what if the old planks are used to build a second ship? Which one is the real one? This paradox has been debated by philosophers for over 2,000 years, and there is no single easy answer. It reveals that our concept of identity is a very slippery and fuzzy one. Some philosophers, the mereological essentialists, would argue that the moment you replace a single essential part, the object ceases to be the original object. Others would argue that identity is based on the object's form and function, its spatio-temporal continuity. As long as the changes are gradual and it continues to exist as a ship in the harbor, it is the same ship. And a third view is that identity is just a human convention, a story we tell. The ship in the harbor is the ship of Theseus, because we all agree to keep calling it that. It is the story, the history, that provides the continuous thread of identity. As we discussed, this has a profound and quiet application to our own sense of self. Are you the same person you were 10 years ago, even though you are made of different atoms and have different thoughts and memories? The ship of Theseus paradox is a quiet, gentle, and deeply personal invitation to contemplate what it truly means to be you. It suggests that our sense of a single, unchanging self might be a beautiful illusion, and that we are, in fact, like Theseus's ship, in a constant, quiet state of renewal and change.
Now let's look at another set of famous paradoxes from ancient Greece. These are the paradoxes of Zeno of Elea, and they deal with the strange, slippery, and seemingly impossible nature of motion and infinity. Zeno's most famous paradox, as we know, is the story of Achilles and the tortoise. The great hero Achilles, the fastest runner in all of Greece, gives a slow-moving tortoise a 100-meter head start. Zeno argued that for Achilles to catch the tortoise, he must first reach the point where the tortoise started. But in that time, the tortoise has moved a little bit farther ahead. Now Achilles must cover that new, smaller gap. But in that time, the tortoise has moved a little bit farther still. Because there are an infinite number of these ever smaller gaps that Achilles must first cross, Zeno argued that, logically, he can never actually overtake the tortoise. Of course, we know from our everyday lives that a fast runner can easily overtake a slow tortoise. So what is wrong with Zeno's logic? The paradox is a beautiful and quiet illustration of the strange and counterintuitive nature of the infinite.
The modern solution to this puzzle comes from the mathematical field of calculus and the concept of a convergent series. It's true that Achilles has to cross an infinite number of smaller and smaller gaps, but the time it takes to cross each of these gaps also gets infinitely smaller. And the crucial insight is that the sum of an infinite number of these ever-decreasing time intervals is not infinite. It is in fact a finite amount of time. So Achilles does overtake the tortoise, and he does so in a finite and usually very short amount of time. The paradox is a quiet, beautiful puzzle that forced mathematicians for centuries to grapple with the strange but powerful logic of infinity. It shows that our common-sense intuition about an infinite series is often wrong.
And now for our final chapter in this philosophical gallery, let's explore a more modern and very quiet paradox. This is a puzzle about knowledge and prediction, known as Newcomb's paradox. Imagine the scene: a super-intelligent being, a friendly alien from another world, who has the proven ability to predict your choices with almost perfect accuracy, presents you with two boxes. Box A is transparent, and you can see that it contains $1,000. Box B is opaque. You cannot see what is inside. The alien now tells you that you have a choice. You can either choose to take both Box A and Box B, or you can choose to take only Box B. And here is the catch. The alien explains how they have set up the game. Yesterday, they made a prediction about which choice you were going to make. If they predicted that you would choose to take only Box B, they placed $1 million inside Box B. If they predicted that you would choose to take both boxes, they put nothing inside Box B. And remember, their predictions are almost always correct. So what do? The paradox arises because there are two seemingly logical but completely contradictory ways to think about the problem. The first is the logic of expected utility. The alien has already made its prediction and has already either put the $1 million in Box B or not. The contents of the box are already set. So at the moment you are making your choice, you should choose to take both boxes, because no matter what is in Box B, taking both will always give you an extra $1,000. But the second way to think about it is the logic of strategic dominance. You know that the predictor is almost always right. So if you choose to take both boxes, the predictor will have almost certainly predicted this and will have left Box B empty, so you will only get $1,000. But if you choose to take only Box B, the predictor will have almost certainly predicted this and will have placed the $1 million inside it. So you should choose only Box B. Which logic is correct? This quiet, simple puzzle has been debated by philosophers and mathematicians for decades, and there is no consensus. It is a beautiful, quiet paradox that pits our ideas of free will against the idea of a predictable universe.
All right. We have journeyed through the scientific possibilities of the multiverse and the philosophical labyrinths of simulated realities and strange paradoxes. For our final and most abstract chapter in this quiet exploration tonight, we will descend into the realm of the void itself. We will contemplate the nature of nothingness, the limits of our own minds, and the very meaning of the question we started with. We begin with a simple, quiet question. What do we mean when we say nothing? This brings us to a beautiful and profound distinction: the difference between the physicist's nothing and the philosopher's nothing. When a modern physicist talks about nothing, they are usually talking about the vacuum of space. But as we have learned, the quantum vacuum is not a true state of nothingness at all. It is a seething, bubbling,
and deeply complex place. It is the quantum foam, a sea of quantum particles and antiparticles constantly popping into and out of existence for fleeting moments. The quantum vacuum is filled with energy, with potential, and with all the fundamental fields that govern our reality. The physicist's nothing is in fact a very rich and interesting something. In fact, some theories, like the one proposed by the physicist Lawrence Krauss, suggest that our entire universe could have emerged from this kind of nothing. This is the idea that the total energy of the universe, the positive energy of all its matter and radiation, and the negative energy of its gravitational field, might add up to exactly zero. If this is true, then the universe could have emerged from a random quantum fluctuation in this pre-existing quantum vacuum, without violating the law of conservation of energy. It would be the ultimate free lunch. In this view, outside our universe is just an eternal, quiet, and potent quantum vacuum.
But this is not what a philosopher means when they talk about nothing. The philosopher's nothing is a much more absolute and much more difficult concept. It is not just the absence of matter and energy, it is the absence of space, of time, of physical laws, of mathematical logic, and of existence itself. It is pure, absolute, and total non-being. Can such a state even be conceived of? The moment we try to think about it, we are forced to imagine a space for it to exist in, which violates the very idea of it. It is a concept that seems to lie at the very edge of what our minds are capable of imagining. This quiet, deep distinction is crucial for our question. When we ask, what's outside the universe? We must first define what we mean. If the universe is just our bubble of space-time, then outside could be a quantum vacuum or a multiverse. But if the universe is, by definition, the totality of all existence, then asking what is outside of all that is becomes a much more difficult and perhaps a much more meaningless question. This brings us to our next quiet, contemplative chapter. What if the problem is not with the universe, but with our own minds and the language we use to describe it? This is the idea of the limits of language and thought. Perhaps the question, what's outside the universe, is not a scientific question at all, but a semantic error, a failure of our human language to properly describe a reality it was not evolved to comprehend. Let's explore this with a simple, quiet analogy.
The classic analogy for this is the question, what's north of the North Pole? It sounds like a real question. It has a question mark at the end, but it is in fact a meaningless question. The concept of north is defined entirely by the surface of the sphere we call Earth. It is the direction you travel to get to the North Pole. Once you are standing on the North Pole, the concept of north ceases to have any meaning. Every direction you could possibly point is south. There is no north of the North Pole because the term itself is defined by the limits of the system you are in. It's possible that our question, what's outside the universe, is a similar kind of logical error. The very concepts of outside and inside, of before and after, are concepts that are defined within our universe of space and time. The universe, by its very definition, is the totality of all space, all time, all matter, and all energy.
So to ask what is outside of all that is might be a fundamentally meaningless question. There might be no outside to the universe, not because it has a wall, but because the very concept of outside is a property of the space that is contained within it. This is a quiet, and for some, a slightly unsatisfying conclusion, but it is a deeply profound one. It suggests that the ultimate boundary we are encountering is not a physical one, but a conceptual one. It is the limit of what our language and our minds can meaningfully express. Our brains, after all, did not evolve to contemplate the nature of cosmic origins or extra-universal realities. They evolved to help us find fruit, avoid predators, and navigate the social complexities of a small tribe on the African savanna. It is a miracle that we can understand as much about the universe as we do. But it is entirely possible that there are aspects of reality that are just fundamentally and forever beyond our ability to comprehend.
And that brings us to our final, quiet, and deeply humble conclusion on this long and strange journey. We have explored the observable universe, our small, visible bubble of reality. We have journeyed through the speculative but scientifically grounded possibilities of the multiverse with its infinite bubbles, hidden dimensions, and branching timelines. We have descended into the deeply strange philosophical labyrinth of the simulation hypothesis, and we have ended with a quiet contemplation of the limits of our own minds. So what is the final answer to our great question? The quiet truth is, there is no final answer. There is only a beautiful, rich, and ever-expanding landscape of possibilities. The question, what's outside the universe, is not a question with a single, correct answer that we are waiting to discover. It is a prompt. It is an invitation. It is a tool for exploring the very boundaries of our knowledge and our imagination. And that, I think, is a wonderfully comforting and peaceful thought. It means that the journey of discovery will never be over. There will always be new ideas to ponder, new theories to explore, and new, quiet, and beautiful ways to think about our place in the cosmos. So as you drift off to sleep tonight, let your mind be at peace with this profound and beautiful uncertainty. The universe does not owe us simple answers, but it gives us the incredible gift of being able to ask these grand, quiet, and wonderful questions. And the value is not in finding a definitive destination, but in the peaceful, quiet, and deeply awe-inspiring act of the journey itself.